folks, Avery the Applications Astronaut back talking to you about AP questions involving applications of derivatives. Now here's my question. What's an astronaut's favorite day of the week? That's going to be Sunday.
Now question 1 says let f be the function defined by f of x is equal to ln of x over x. What is the absolute maximum value of f? So, a couple things. Anytime it says what is the absolute maximum value or absolute minimum value of a given function, it's talking about the y value. So in this case, we have to find the x value at which we have an absolute maximum, plug that into the given function, and that will be the absolute maximum value of our function. Now, how do we find an absolute maximum? Well, anytime you're looking for relative maxes or mins, we need to find the critical numbers of our function. The critical numbers of a function occur at whatever x values cause the derivative of your function to either equal 0 or not exist. If the derivative of your function equals 0, that means the slope of the tangent line to the function equals 0, meaning your function has reached a relative min or a relative max. If the derivative does not exist, your function may have a cusp or a corner where the derivative does not exist, but that value could still be a max or a min value, so we have to check. So, in order to find the critical numbers, we're looking for wherever the derivative equals 0 or does not exist. So we have to take the derivative of our function. Now, how do you take the derivative of a function being divided by another function? Well, anytime you're taking the derivative of a quotient, you need to use the quotient rule. The quotient rule says you take the derivative of the numerator, multiply it to the denominator, then subtract the numerator times the derivative of the denominator all over the denominator squared. The derivative of ln of x is going to be 1 over x. The derivative of x is going to be 1. 1 over x times x, these two x's cancel each other out. This just turns into a 1. Negative ln of x times 1 is just still negative ln of x, and we have our derivative. Again, critical numbers occur at whatever x values cause the derivative to equal 0 or not exist. Are there any x values that would cause this derivative to not exist? AKA, are there any x values that would cause the denominator to equal 0? Yeah, at x is equal to 0, this derivative would not exist because it would have a denominator equal to 0. We then look, are there any x values that would cause this derivative to equal 0? So I set this derivative equal to 0 and solve for x. In order to get a rational function equal to 0, the numerator is the only thing that has to equal 0. So I just set the numerator equal to 0 and I solve for x. How do I solve for x? I'm going to add ln of x to both sides, and then what I'm going to do is on both sides of the equation, I'm going to go e to the ln of x is equal to e to the first. The reason I do that is because on this side, e to the ln of x, those two things cancel each other out and I'm just left with x. On this side, I get e to the first. So the x values that I'm going to have my critical numbers at are going to be 0 and e. So I need to then test each of those critical numbers by plugging them into the original function and seeing what y value I get. Whatever the greatest y value is that comes out is going to be the absolute maximum value of our given function. So let's plug in each of these x values to our original function, see what we get. We plug in 0 first. If I plug in 0, oh, I got 0 in the denominator, which means this is undefined, meaning that this is not going to give us a cusp or a corner. This is going to give us an asymptote at x is equal to 0. So we then plug in e to the original function for x and we simplify and we end up getting ln of e, which we know is 1 over e. So f of e, the function when we plug in e for x, gives us a y value of 1 over e, and that's our only critical number that isn't an asymptote. So this has to be our absolute maximum value on that given function, meaning b is your answer. Question 2 says the graph of the function f is shown in the figure below. For which of the following values of x is f prime of x positive and increasing? Now this question is trying to trick you in a couple different ways. The first is that we are given the graph of f, not the graph of f prime. Typically when you're looking for where f prime of x is positive and increasing, you're given the graph of f prime. But here's the graph of f. So it's actually a little bit easier. Now, we have to figure out what do each of these mean. Well, when f prime of x is positive, that means the slopes of the lines tangent to the given function are positive, meaning your original function is going to be increasing. So we are looking for where the original function f is increasing. We're also looking for where f prime is increasing. So where's f prime increasing? Well, that means the slopes of the lines tangent to the given function are increasing, meaning that the second derivative of your given function is positive, meaning that your original function would be concave upward. So this right here is code for where is the original function increasing and concave upward. So now we look at the graph of f and determine at which x value here is it both increasing and concave upward. Well, at x is equal to a, we are decreasing and concave downward, so clearly not there. At x is equal to b, we have a cusp, meaning that f prime doesn't even exist at x is equal to b, so can't be there. At x is equal to c, we are increasing, but it looks like the slopes of the lines tangent to the given function are decreasing, meaning our second derivative would be negative, meaning we're concave downward there. It's not our x value. At x is equal to d, it looks like our function is decreasing, and it looks like it's changing from concave downward to concave upward, meaning there's going to be an inflection point at x is equal to d. So we are decreasing, and f double prime is 0. Then we look at x is equal to e, and we see that our function is increasing, and the slopes of the lines tangent to the given function are increasing as well, meaning the second derivative is positive, meaning it's concave upward there also. So since we are increasing and concave upward at x is equal to e, we know that f prime has to be positive and increasing at x is equal to e. Question 3 says the graph of f prime, the derivative of the function f, is shown above. Which of the following statements must be true? So we're going to go through each of these statements one by one and determine which has to be true. So let's start with the first one. F has a relative minimum at x is equal to -3. So the first thing you need to remember is that we are given the graph of the derivative. In the graph of the derivative, the y values here correspond to the slopes of the tangent lines to your original function. So if we're looking for a relative minimum, we need the y values of the graph of your derivative to go from negative to positive, because that would mean the slopes of the lines tangent to your original function would go from negative to positive, meaning it would create a relative minimum. So at x is equal to -3, do the y values of your derivative go from negative to positive? Yes, they do, meaning that the slopes of your original function go from negative to positive, meaning that your original function would have a relative minimum at x is equal to -3. Let's move on to the next one. So this says the graph of f has a point of inflection at x is equal to -2. So your first instinct would be to look up here and say, oh, at x is equal to -2, your graph changes from concave downward to concave upward. So yeah, there would be an inflection point here. But no, this says the graph of f has a point of inflection. This is the graph of f prime. Remember, our original function f is going to have an inflection point anywhere where it changes from concave downward to concave upward, or concave upward to concave downward. And that's going to occur anywhere where the second derivative of our original function changes from negative to positive or positive to negative. Meaning, if we're looking at the graph of f prime, it's where the derivative of our derivative, or the second derivative, changes from positive to negative or negative to positive. So where does the slope of the graph of f prime change from positive to negative or negative to positive? Well, the only x value at which the slope of f prime, or the derivative of our derivative, or the second derivative, changes from positive to negative, would be at x is equal to 0. So that's going to be the only inflection point of the graph of f, meaning that there will not be an inflection point at x is equal to -2. Let's move on to the last statement that says the graph of f is concave down for 0 is less than x, which is less than 4. So is the graph of f, our original function, concave down on the interval from 0 to 4? Now, we said that the original function f is going to be concave down anywhere where the second derivative is negative. So we look at the graph of f prime, and we're trying to figure out where is the slope of f prime, or the derivative of our derivative, negative. So where are the slopes of the lines tangent to f prime negative? Well, that would be from x is equal to 0 to x is equal to 4. The slopes of the lines tangent to the graph of f prime here are all negative from x is equal to 0 to x is equal to 4, meaning that your graph of your original function would have a second derivative that was negative from x is equal to 0 to x is equal to 4, meaning that your graph of f would be concave down on that given interval. So the two statements that must be true would be 1 and 3, meaning your answer would be E over here. Now question 4 says the function y is equal to g of x is differentiable and increasing for all real numbers. On what intervals is the function y is equal to g of x cubed minus 6x squared increasing? So to figure out the intervals where a function is increasing, we have to make a sign chart. And since it's just wanting you to figure out the intervals where a function is increasing, it just has to be the first derivative sign chart. We don't have to worry about the second derivative sign chart because it doesn't say anything about concave upward or concave downward. So to make a sign chart for the first derivative, we need to figure out our critical numbers. So how do I figure out the critical numbers of this function? Well, the critical numbers occur wherever the derivative is equal to 0 or does not exist. So what we need to do is figure out the derivative of this given function. How do I take the derivative here? Well, I have a function x cubed minus 6x squared within a function g. So this requires the chain rule. So I'm going to take the derivative of the outer function first. Derivative of g is just going to be g prime of x cubed minus 6x squared. That stays the same. But then I multiply by the derivative of my inner function. The derivative of x cubed minus 6x squared is going to be 3x squared minus 6 times 2x to the first, so minus 12x. Now I have my derivative of this function. Now that I have my derivative, I need to find my critical numbers. Remember, critical numbers occur wherever the derivative is either equal to 0 or does not exist. Are there any x values that would cause this to not exist? No, there's no denominator, so we're good to go. All we have to do is figure out where this equals 0. So for this to equal 0, we have two things being multiplied together, meaning either this is equal to 0 or this is equal to 0. So we can split that up using the zero product property. Now let's determine where g prime of x cubed minus 6x squared equals 0. So this looks super complicated, like I'm going to have to factor something or do some type of integration. No, all I have to do is look at this in the original question where it says the function g of x is differentiable and increasing for all real numbers, meaning g prime is always going to be positive. No matter what you plug in here, g prime, the derivative of our function, always has to be positive because g of x is always increasing for all real numbers. So since g is always increasing, g prime always has to be positive, meaning it can never equal 0. Over here, how do I figure out what x values cause this to equal 0? Well, I need to factor out a 3x from each of these terms, and now I have this times this equals 0, so I can use the zero product property again and say either 3x has to equal 0 or x minus 4 has to equal 0. I solve each of these for x, divide both sides by 3 over here, add 4 to both sides over here, and I have my two critical numbers. So I'm now going to create a sign chart for the first derivative. And when I do that, I look and see, are there any domain restrictions for my interval? No. So I'm going to go from negative infinity to positive infinity and break it up based on these critical numbers. So my first interval is going to go from negative infinity to 0. My next interval is going to go from 0 to 4. And then lastly, I'm going to go from 4 to infinity. Now we're going to choose test x values on each of these intervals to plug into our first derivative for x. We're then going to simplify those and determine what the sign of the number is that we get out. If we get out a positive number, that means the function is going to be increasing on that given interval. If we get a negative number, that means the function is going to be decreasing on that given interval. So on this given interval, let's choose -1 to plug into our first derivative for x. Now you may think, how do I plug in -1 over here? How do I even simplify that? Well, if you recall, g is differentiable and increasing for all real numbers, meaning g prime, the derivative of g, has to be positive no matter what you plug in here because g is always increasing. So we don't even have to evaluate this part of the derivative. Just know that whatever you get here, you're multiplying it by a positive number. So we're just going to evaluate this right here, and then whatever this is, that's going to determine the sign of our derivative. So we're going to plug in -1 for x here and here. We then simplify and we get 15. So this over here equals 15. We're then multiplying 15 to a positive number, which means it stays positive. Because it's positive, that means that the derivative of this function on this given interval is positive, meaning that the slopes of the lines tangent to this function on this given interval are positive, meaning that this function on this given interval is increasing. Doing the same thing here. Let's choose a x value on this interval to plug into our derivative. How about 1? If I plug in 1 to the derivative over here, remember, no matter what this is going to be positive. When I plug in 1 for x over here, I get -9. So a negative number times a positive number is going to be negative, meaning that the derivative of this function on this given interval is negative, meaning that the slopes of the lines tangent to this function on this given interval are negative, meaning that this function on this given interval is decreasing. Then we're going to pick a test x value on this interval and plug it into the derivative. How about 5? If I plug in 5 to our derivative over here for x and I simplify, I end up getting 15 times some positive number. Now 15 times a positive number is going to be a positive number, meaning the derivative of this function on this given interval is positive, meaning the slopes of the lines tangent to this function on this given interval are positive, meaning that this function on this given interval is increasing. Therefore, the function is going to be increasing on the intervals from -infinity to 0 and 4 to infinity, and they will be decreasing on the interval from 0 to 4. Therefore, we can say that our answer is going to be A over here, and we're done. Now, question 5 says the figure above shows the graph of f prime, the derivative of a twice differentiable function f on the interval from -3 to 4. The graph of f prime has horizontal tangents at x is equal to -1, x is equal to 1, and x is equal to 3. The area of the regions bounded by the x-axis and the graph of f prime on the intervals from -2 to 1 and 1 to 4 are 9 and 12 respectively. So we're going to answer each part of this question. Let's start with A. Part A says find all x coordinates at which f has a relative maximum. Give a reason for your answer. So here we are given the graph of f prime, the derivative of our function. Now remember, in the graph of the derivative, the y values correspond to the slopes of the graph of your original function. Anywhere where the graph of f prime is above the x-axis, that's where your original function has positive slopes, meaning your original function would be increasing. Anywhere where the graph of the derivative has negative y values, anywhere where it's below the x-axis, your original function has slopes that are negative, meaning your original function would be decreasing. So to find a relative maximum of the graph of f, you're looking for the graph of f to go from increasing to decreasing at that specific value, meaning you're looking for the graph of f prime to go from positive y values to negative y values. And where does that happen? That happens at x is equal to -2. Because the graph of your derivative goes from positive y values to negative y values, your original function goes from increasing to decreasing. Meaning, by the first derivative test, your original function would have a relative maximum at x is equal to -2. Now part B says on what open intervals contained in the interval from -3 to 4 is the graph of f both concave down and decreasing? Give a reason for your answer. So again, we are given the graph of the derivative of your function, meaning that the y values of the graph of the derivative correspond to the slope of your original function. So anywhere where the graph of the derivative is above the x-axis, anywhere where it has positive y values, the graph of your original function will have positive slopes, meaning it will be increasing. Anywhere where the y values of the graph of the derivative are negative, anywhere where it's below the x-axis, that's where the graph of your original function will have negative slopes, meaning it will be decreasing. But we also need f to be concave down as well. So how do we determine concavity with the graph of the first derivative? Well, to be concave down, that means the second derivative of your function has to be negative, meaning the derivative of your derivative has to be negative, or the slope of your derivative has to be negative. So we're looking for anywhere where the graph of f prime has a negative slope, because that would be the slope of your derivative, or the derivative of your derivative, or the second derivative. So where does that occur? Well, we know the graph of f prime has a negative slope from -3 to -1, and then again from 1 to 3. But we need it to be both decreasing and concave down. So where is the graph of f prime? Below the x-axis, meaning it has negative y values, meaning your original function is decreasing. And where does the graph of f prime have a negative slope, meaning the derivative of your derivative is negative, meaning your second derivative of your function is negative, so your graph would be concave down. Well, that would be on the intervals from -2 to -1. We're below the x-axis and we have a negative slope. And then again, from x is equal to 1 to x is equal to 3, we are below the x-axis and we have a negative slope. Part C says find the x-coordinates of all points of inflection for the graph of f. Give a reason for your answer. Now remember, inflection points occur wherever the graph of your original function changes from concave down to concave up, or concave up to concave down, meaning it's where the second derivative changes from negative to positive or positive to negative. So how do we interpret the second derivative from the graph of the first derivative? Well, we already said that the second derivative is just the derivative of your derivative, or the slope of your derivative. So the second derivative corresponds to the slope of the derivative graph. So the original function f is going to change concavity anywhere where the slope of the derivative graph changes sign. So anywhere where the derivative graph changes from increasing to decreasing or decreasing to increasing. So where does the slope of our derivative graph change sign? Where does the derivative of our derivative, or our second derivative, change sign? Well, the graph of f f prime, the graph of our derivative, starts off with a negative slope, meaning the derivative of our derivative is negative, meaning the second derivative is negative, meaning our original function f would be concave downward from x is equal to -3 to x is equal to -1. Then from x is equal to -1 to x is equal to +1, the slope of our derivative graph, or the derivative of our derivative, or our second derivative, becomes positive, meaning that our original function f changes to concave upward, because at x is equal to -1, the graph of f prime changes from a negative slope to a positive slope. That means in our original function, the graph of f is changing from concave down to concave up, meaning at x is equal to -1, there's going to be an inflection point. Same thing at x is equal to 1. The graph of f prime changes from a positive slope to a negative slope, meaning that the derivative of our derivative, or the second derivative, changes from positive to negative. Because of that, we know our original function is changing from concave upward to concave downward, meaning there's going to be an inflection point at x is equal to 1 as well. Lastly, at x is equal to 3, we again have the graph of f prime go from a negative slope to a positive slope, meaning the derivative of our derivative, or the second derivative, changes from negative to positive, meaning our original function changes from concave downward to concave upward. So there's also going to be an inflection point at x is equal to 3. Now question 6 says let f be a function with a derivative given by f prime of x is equal to x cubed minus 8x squared plus 3 over the square root of x cubed plus 1 for -1 less than x, which is less than 9. At what value of x does f attain a relative maximum? Now take a look at what we're given. We're given the derivative of our function, and we're asked where the original function has a relative maximum. Also take a look at our answer choices. Most of them are rounded to the nearest thousandth, meaning this will likely be on the calculator portion of the AP test. So what you're going to have to do is you're going to have to use your graphing calculator to answer this question. The way you do this is you create the graph of the first derivative. So we entered this into our graphing calculator, and we have the graph of the first derivative. Now remember, relative max and min values occur at whatever x values cause your derivative to equal 0. So here we have critical numbers at x is equal to -0.591, x is equal to 0.638, and x is equal to 7.953. That's why those three are possible answers. That's no coincidence. Now we need to figure out at which of these three x values does our original function have a relative maximum. So we remember the first derivative test. The first derivative test says your original function f will have a relative maximum anywhere where it goes from increasing to decreasing, meaning anywhere where the slopes of the tangent lines to the curve go from positive to negative. And remember, in the graph of the derivative, the y values correspond to the slopes of the tangent lines to your original function. So we're looking for anywhere on the graph of f prime where the y values go from positive to negative. And where does that happen? That only happens at x is equal to 0.638. That's why our original function f will have a relative maximum at this value, because the slopes of the lines tangent to your original function go from positive to negative. The y values here go from positive to negative, meaning your function goes from increasing to decreasing at that given x value. Now question 7 says John needs to enclose an area with a fence. He has 50 feet of fencing available, and a permanent straight wall of infinite length exists on one side. What dimensions of the fence will give John the largest possible area? So right away, the first light bulb that should go off in your head is you're being asked what dimensions will give John the largest possible area, meaning we are trying to maximize the area, meaning that this is an optimization problem. So we need to go through our steps for an optimization problem. The first is to make a sketch and label any constant measures with a number and anything you're trying to optimize with a variable. Well, we are trying to optimize the dimensions, and they already give us each of those variables, the length and the width of our given fence. So we can move on to the next part, which is to state all given quantities and quantities to be determined. So we'll start with given quantities. What are we given? We're given that John has 50 feet of fencing available, meaning that the perimeter of this fence, because we don't have to include the wall, the perimeter of the fence has to equal 50 feet. Next, we need to know what quantities are to be determined. What are we even trying to find here? Well, it says what dimensions of the fence will give John the largest possible area. So we're trying to find the dimensions of this fence, the length and the width of this fence. Now we can move on to step 2, which is to state our primary equation, the equation that we are trying to optimize. So what are we trying to optimize? We're trying to optimize the area of this rectangle here. Now, because it's the area of a rectangle, we're going to use the area area of a rectangle formula as our primary equation. Area is equal to length times width, or in this case, x times y. Now that we have our primary equation, a is equal to x times y, we need to rewrite it so it only has one independent variable, because our plan is to take the derivative of this to find our critical numbers and then set that equal to 0 and solve for one of our variables. Now, it's much harder to do if there's two independent variables. So how do we rewrite it so it only has one independent variable? We look back at what we were given. We were given that John has 50 feet of fencing available, meaning that the perimeter here would have to equal 50 feet, meaning that the width plus the length plus the width would have to equal our perimeter, or in this case, 50 feet. We have variables to describe the width and the length, right? The width is y, so that goes in here and here, and the length is x, so that goes in here. We then simplify y plus y gives you 2y, and now we can solve for one of these variables. So then we can plug in what that variable is equal to up here, creating an equation with only one independent variable. So you can solve for x or y, it doesn't matter. You'll get the same answer either way. I think this looks like it's easier to solve for x, right? I just subtract 2y on both sides. Now I know that x is equal to 50 minus 2y, so all I have to do is take 50 minus 2y, plug it in this equation up here for x, and I only have one independent variable now, just y. Now that I have my primary equation with only one independent variable, I can find the critical numbers of this equation by taking the derivative of this equation and setting it equal to 0 and solving for y. To do that, I would want to distribute this first before I take the derivative, so let's multiply this y to the negative 2y and to the 50. We are now ready to take the derivative over here, and we're just going to take the derivative with respect to our independent variable, which in this case is y. So when we take the derivative over here, derivative of 50y, the 50 just hops out front. You take the derivative of y, that just turns into 1. So it'll be 50 times 1, which is 50. And then over here, the derivative of negative 2y squared, the negative 2 stays out front by the constant multiple rule. Then you take the derivative of y squared using the power rule, becomes 2y to the first power. Multiply the 2 to the negative 2 out front, and you get negative 4y to the first. Now we have the derivative of our given equation with respect to y. So to find the critical numbers, all we have to do is set the derivative equal to 0 and solve for y. So to solve this for y, all we have to do is just add 4y to both sides, divide both sides by 4, and we get y is going to be equal to 12.5 feet. So that is the width of our given enclosure. Now, we ask ourselves, does this answer make sense? Is it 0? Is it negative? No, it's positive 12.5 feet. So that makes sense. That's totally within the realm of possibilities, since the perimeter just has to equal 50 feet. Now, we have found the width of our given enclosure. We need to find the length now. So how do we find the length? How do we find x? Well, earlier on, didn't we solve for x so that we could substitute it in and only have one independent variable? Yeah, we found that x was actually equal to 50 minus 2y. That's why we were able to substitute that in over here. And now that we know y, we can just take that 12.5, plug it in for y here, and solve for x. So negative 2 times 12.5 is going to be negative 25. Then 50 minus 25 gives you 25, meaning the length of our enclosure here is going to be 25 feet. Now, we were asked a word problem, so we need to answer in a sentence. A fence with a length of 25 feet and a width of 12.5 feet would have a maximum area with 50 feet of fencing available. Now question 8 says the measurement of the circumference of a circle is found to be 64 centimeters with a possible error of 9/10 of a centimeter. Part A says approximate the percent error in computing the area of the circle. Then part B says estimate the maximum allowable percent error in measuring the circumference if the error in computing the area cannot exceed 3%. So we're going to deal with part A first. This is approximate the percent error in computing the area of the circle. So anytime you see error like this, you know this is an error question. And error questions, we solve the same way we would a related rates problem. Instead of rates, we're dealing with error. Now, the key difference between a related rates problem and an error problem is that we don't implicitly differentiate. We just differentiate like normal. So let's go through the steps. The first step in a related rates problem or error problem, we have to determine the given quantities. What do they give us here? Well, we are given that the measurement of the circumference of the circle is found to be 64 centimeters. So C is equal to 64. We also know this measurement has a possible error of 0.9 centimeters, meaning the change in C or delta C, or equivalently DC, has to be between negative 0.9 and positive 0.9, because it could be 9/10 of a centimeter more or 9/10 of a centimeter less. Now, we can move on to the next part, which is to state all quantities to be determined. What are we trying to find here? Well, it says approximate the percent error in computing the area of the circle. Well, we know three types of error. We know propagated error, relative error, and percent error. Propagated error in computing the area of the circle would just be dA. Relative error in computing the area of the circle would be dA over A. And then percent error, which is what we're trying to find in computing the area of the circle, would be the relative error times 100, or dA over A times 100. So this is what we're trying to find. We can then move on to step 2, which is to state our equation. What equation are we going to use that we can take the derivative of and will help us find dA over A times 100? Well, if we're looking for the percent error in computing the area of the circle, maybe the area of a circle formula should be our equation. Perfect. So now, before we move on to the next step where we take the derivative, I want you to notice something. If I were to take the derivative of this, I would get dA over dr is equal to 2 pi r. But look at what we're given. We're given everything in terms of the circumference. We're given the circumference measurement, and we're given dc, or delta c. Well, how do I get c into this equation? I need to rewrite the radius here in terms of circumference. That way, when I take the derivative, I can get dA over dc is equal to whatever this is in terms of c. That way, I have a dc that I can plug in, and I have a c that I can plug in. So, how do I rewrite the radius in terms of the circumference? Well, I know that the circumference of a circle formula is 2 pi r. So if I wanted to solve this for the radius, I could just divide both sides by 2 pi. I get the radius is equal to the circumference over 2 pi. Now, why does this help me? Because I can now take c over 2 pi, plug it in the area formula for r, and I no longer have r. I have c. So when I take the derivative eventually, I can plug in these given values. So let's simplify this. If I were to square each of these, I square the numerator and denominator. I then multiply. This pi cancels out with one of these pi's in the denominator. I have my area formula in terms of circumference. So I can then move on to the next step where I differentiate both sides with respect to the circumference, c, and find dA, the differential of A, or the propagated error in computing the area of the circle. So let's take the derivative of this equation. To take the derivative here with respect to c, or the circumference, I'm going to take the derivative over here, which is going to be dA over dc. When I take the derivative on this side, I'm going to rewrite this as 1 over 4 pi times c squared. The reason I do that is because now when I take the derivative, I see that 1 over 4 pi is just a constant I can leave out front, and I can just take the derivative of c squared using the power rule. So I get 2c to the first times that 1 over 4 pi, which I can rewrite like this. Now the 2 and the 4 simplify to just 1 over 2, and I have dA over dc is equal to c over 2 pi. But I'm trying to solve for dA. So to get dA by itself, I just multiply both sides by dc, and I have solved for dA. Now, how does this help us? Well, I'm trying to find dA over A times 100. So I have an equation solved for dA. I also have an equation solved for A. So what I can do then is substitute in for what I know. I know that dA is equal to c dc over 2 pi, so I'm going to plug that in there. I know A is equal to c squared over 4 pi, so I'm going to plug that in there. Now, how does that help us? Well, I can simplify this by rewriting it as c dc over 2 pi. Instead of divided by this fraction, it's going to be multiplied by the reciprocal. Now, this 4 and this 2 cancel each other out, just leaving a 2 here. This pi and this pi cancel each other out. This c cancels out with one of these c's down here, so I can rewrite dA over A as 2 dc over c. Now, how in the world does that help us? Well, it's because I already know what c and dc are. dc is going to be plus or minus 0.9. c is equal to 64. So I can plug in each of those values, simplify, and I get that dA over A is approximately equal to plus or minus 0.028125. Now, that's dA over A. That's the relative error. I'm trying to find the percent error, so I need to multiply that by 100. My percent error in computing the area of the circle is approximately equal to 2.812%. So now we can move on to part B, which wants us to estimate the maximum allowable percent error in measuring the circumference. So in this case, it would be dc over c times 100. That's what we're looking for. If the error in computing the area cannot exceed 3%. So the percent error in computing the area, dA over A times 100, has to be less than or equal to 3%. So here's what we're trying to find. We need to find dc over c times 100 if dA over A times 100 has to be less than or equal to 3%. Well, if we know dA over A times 100, the percent error in estimating the area of the circle has to be less than or equal to 3%, how do we figure out what DC over C times 100 is? Well, is there any way we could substitute something in for this? Yeah, didn't we solve for that earlier on? dA over A is equal to 2DC over C. Oh, look at that. And that's kind of what we were looking for. So let's go ahead and take 2DC over C and plug that in for dA over A here. And when I do that, I get something that looks like this. Now again, we're solving for DC over C times 100, so we need to get rid of this 2. So I can either divide both sides by 2 or multiply both sides by a half. I end up getting that DC over C times 100, or the percent error in measuring the circumference of the circle, has to be less than or equal to 1.5% if the error in computing the area cannot exceed 3%. If dA over A times 100 has to be less than or equal to 3%, then DC over C times 100 has to be less than or equal to 1.5%. And you're done.